Dear audience, dear conference committee, thank you very much for the opportunity to present our work benchmarking AutoML-supported lead time prediction on behalf of Yannick Bender and our professor Jivka Ovcharova. My name is Martin Trat and we work at the FZI Research Center for Information Technology. The work was done within the context of the research project with the name ALTO, which is sponsored by the Federal Ministry of Education and Research. It is actually a follow-up research for the publication Prototyping Machine Learning Supported Lead Time Prediction using AutoML. First, I'm going to introduce our motivation to you, show some of the works from the body of related works, show the case studies we used to evaluate our method, show how we designed our method and application, and finally we are going to show some of the results, the best model, give a conclusion and a outlook. The goal of our work is to provide reliable lead times for job scheduling, which is in practice still very manually driven, so based much more on experience rather than data. Lead times are difficult to predict. Nevertheless, they could be of high value for small and medium-sized enterprises to keep up with shorter development cycles and to provide an input for the rather complex optimization problem of job scheduling. Also, we want to evaluate automated machine learning in this work, and we would like to ask the question whether the benchmarked AutoML solutions can outperform manual predictions. We would like to know what tasks along the machine pipeline are supported by AutoML and how good does AutoML work with the imperfection of real-world data. When reading existing works on the topic of lead time prediction, one will see that many algorithms have been evaluated. However, tree-based methods such as regression or decision trees or randomized forests stand out with their very good performance. When informing oneself about automated machine learning, it is advocated that these methods support non-experts, so people without experience on data science, and they are able to explore many algorithms in an automated fashion. In this work, we evaluated 3 implementations of automated machine learning, which are TPART, H2O AutoML, and AutoKeras. However, there are more implementations out there. Talking about our case studies, we evaluated data from 2 companies, let's call them A and B. Company A produces forging parts, and both company A and B work in the make-to-order domain. Company A has 22 unique production processes. Among them are CNC operations, sawing, forging, and comparable ones. We can use 29 feature columns from that data and have about 100,000 data points, which cover the years 2019 to 21, at least partially. Company B does produce tools and mold designs, has with 108 production processes, some more also involving CNC operations. They also do casting, smoothing, and comparable operations. From their data, we can use 20 feature columns, and we have far less data for Company B, roughly 13,000 data points there, which cover basically the years 2019 and 2020. Among the feature columns we have a lot of categorical ones, basically a lot of string data, and we observed a high share of outliers and errors, which might also be due to manual data gathering. Some Timestamps, for example, are gathered via barcode scanning, so which are prone to human error. And as these companies do some outsourcing as well, there are some data missing as well. How did we design our method and especially our data pipeline? Initially, we transformed the data. We tried to impute missing values using heuristics and plausibility checks. We did formatting of the primarily string-based data, and we did conversion operations on time-related data. We filtered out what we considered as outliers using interquartile range methods, and we ended up with about 80% of company A's data and 92% of company B's data available for training. We used label encoding consistently as our encoding mechanism. However, if AutoML implementations provide some kind of encoding solution, we also tested this on top. For the data selection, we relied on a traditional 80-20 train test split, and we only used unique features. For our training, we set a 60-minute time limit where the implementation did not provide any means of early stopping or maximum number of tries. And we, regarding H2O AutoML, separated between deep learning and non-deep learning machine learning methods, as you will see on the next slide. And we used the mean absolute error as our optimization metric. Apart from that, we also defined a very simple mean model, which basically just outputs the mean of all lead times of a given process, which needs a lead time. And we used this as a baseline to compare to. Now let's look at achieved results. In the 4 rightmost columns, you will see our AutoML-based approaches, namely Tpot, H2O.ai, with no deep learning involved, the same limited to deep learning approaches, and AutoKeras. The 2 columns here show scores associated to the manual prediction and to the simple mean model, as I explained before. When we look at company A's results, we can see that all 4 AutoML-based approaches outperform both simple mean model and the manual prediction. If we look at company B's results, we can see that the results associated to the simple mean model is very comparative to those of our 4 AutoML-based approaches. It is only outperformed by 3 of those 4. But all 4 AutoML-based approaches outperform the manual prediction by far. Across both companies, Tpot produces the best models with an MAE of 29.7 for company A and a MAE of 75.5 for company B. For company A stacking estimator and a extra-cheese regressor is outputted as the best model, and for company B, it is a random forest. Looking deeper into the results of the 2 best models you just saw, we provided some scatter plots. On top right corner, you can see the scatter plot of the best model regarding company A. The horizontal axis shows the actual lead time, and the vertical axis shows the predicted lead times. Green points in this plot symbolize points that produce the 25% lowest errors in lead time prediction. Green points together with yellow points produce the 50% lowest errors. Together with orange points, we lie just below the 75% quantile, and the red points are corresponding to the 25% highest errors. Satisfyingly enough, 75% of our data points, so the green, yellow, and orange colored ones, lie pretty close to our line of perfect predictions. So we have a very high performance on a lot of production processes, and only 25% are scattered very widely around this line. We observed higher rates for specific production processes, which are, for example, sawing and pre-turning. And interestingly, while they make up 17.8% of the entire data set, those make up almost half of the red points in this figure, so of the worst predictions. And when thinking about the original unfiltered data set, it makes up more than 1/4 of the filtered outliers. When looking at company B's best model, you can look at the scatter plot bottom right corner. The same color logic applies. You can see that automated machine learning outputs a model that has a rather narrow range in predicted lead times, lying roughly between 100 and 200 minutes, which comes from the original data distribution. And when applying permutation feature importance calculations, we observe rather low importance values, which makes one think that the features do not carry a lot of information, helping to predict lead times. Also, when looking closer to the original data, we saw that these 108 production steps were not actually unique, but contained some redundancies. And we also observed more opportunities to improve data quality, which fell out of the scope of this work. In order to conclude and to give an outlook for further research, we would definitely support the statement that automated machine learning, as far as we've evaluated, has viable means for producing suitable models for lead time prediction. But we could not observe a constantly high model quality depending on different production processes. And also, as we all pretty much expected, and as it is obvious, also automated machine learning is very highly reliant on good data quality and well-engineered preprocessing methods. Therefore, we would like to further investigate how we could exploit differences between production steps to better predict lead times. Also, we would support the statement that at least evaluated auto machine learning solutions are highly capable of choosing the right algorithms and of solving problems related to training and hyperparameter optimization. But we found that other labor-intensive tasks, as for example data cleaning, understanding, and preprocessing, were only sparsely supported by AutoML. Therefore, we would advocate towards more intelligent, holistic auto machine learning based solutions that also support other tasks than those they are already good at. So this is when we reach the end of this presentation. Thank you very much for your attention. And in case you have any questions, we would be glad if you get in touch with us. For completeness sake, please take note of these references provided on this slide.